Here we are wrapping up with our final bit of plate tectonic evidence. After this video, there are two more videos to watch. They're both about California geology and plate tectonics. The first one has a lot more advanced topics in it near the end, and the second one is made by me and tells you what you really need to know for sure, but I definitely want you to watch both of them. In our last video, we had counted through 4 things that were modern pieces of evidence for plate tectonics, and now we're going to count through 5, 6, 7, 8. So number 5 is the distribution of earthquakes on the globe. If you look at this picture, you'll see all these little red dots represent earthquakes, probably of a magnitude 6 or higher, over maybe a 10-year time period. And you can see, if you are becoming familiar now with the plate boundaries, that this would be the Mid-Atlantic Ridge. This would be the East Pacific Rise, the Pacific Antarctic Ridge, the Southeast Indian Ridge, the Central Indian Ridge, or the Mid-Indian Ridge, Southwest Indian Ridge. And then all of these areas that have extremely dense concentrations of earthquakes would be the trenches, the convergent zones. And if you don't believe me, check this out. Same exact map, but with the plates. Now, if I toggle between them, for example, look at this region here from the Aleutians down to the Japan area. See that? See how those earthquakes look pretty much like they're right on the plate boundaries. And so I can toggle back and forth and you can kind of see that. So that's a really good piece of evidence, because we know that when plates meet, they get stuck, stress builds up, and then eventually there's an earthquake. And that's going to be our next topic after exam number 1. Another thing about earthquakes is that not only are the patterns of earthquakes at the surface telling us about plate boundaries, but seismologists, people who study earthquake waves, have been able to see images below the surface that support plate tectonics. So here's a side view of an area in the Earth. It goes down to 1,600 kilometers depth. And we have the lithosphere in this gray color, and then everything else is the asthenosphere divided into some additional layers that we don't have to worry about. So we have earthquakes at the surface where those two plates are stuck together. That makes sense. But then we also have earthquakes all the way down. That's what these little asterisks are. All the way down to almost 700 kilometers. That's a little more than 400 miles. And normally we would never have earthquakes down here. This is the asthenosphere. The asthenosphere is ductile. It shouldn't have earthquakes. But the reason there's this line of earthquakes identified by 2 different scientists, Wadati and Benioff, so named after both of them, is that this is a piece of solid, cool lithosphere, a plate, going down a subduction zone, and so it's still capable of brittle deformation. It's still capable of breaking. Number 6 is the worldwide distribution of volcanoes. So if you look here, everything that says I or C are lines of volcanoes that are associated with subduction. So we have subduction west of South America, in Central America. We have some at the Juan de Fuca plate going underneath North America. All of these zones out here are volcanoes that are active because of subduction zones. We also have some hotspot volcanoes, and those are not necessarily related to plate tectonics, but they do tell us some information about the plate motion. You'll notice, if you let your eye kind of fall on this map and try to see where the greatest concentration of volcanoes are located, you'll see that they kind of fall all the way around the Pacific Ocean. And for that reason, this area is referred to as the Ring of Fire. And it's the most seismically, which means earthquake, and volcanically active zone in the world, and it's because of all the subduction that's going on. So we have active volcanoes in South America, Middle America. There's a little break here where the San Andreas Fault is, because that's a transform boundary and we don't have volcanoes associated with that. But then we have volcanoes all along the Aleutians and all of these trenches out here that are all created by subduction. So the Ring of Fire is not just a great song by Johnny Cash. Number 7. In modern days, we have GPS, global positioning systems, and we can use it to accurately measure the latitude, longitude, and elevation of any position on the globe. So, for example, we might have something called a benchmark, which is something that geologists put in solid rock Sometimes they're at the peaks of mountains. If you ever climb to a peak, you might see a benchmark. It looks like a gigantic thumbtack. It's about this big, and it has words on it. So the GPS systems can bounce light off of these objects and determine their exact positions, like I said, elevation and latitude and longitude. And they can go back and check it a year later and a year later and a year later, and then they can compare them all. So there's a lot going on in this figure, but if you just look at the blue arrows, which are here, they're showing how things are moving as determined by GPS. And the numbers are centimeters per year. So in the northern part, this is the Reykjavik Ridge, the northern part of the Atlantic Ocean, things are spreading at 1.8 centimeters a year. Down here in the southern Atlantic, things are spreading a little more quickly at 4.1 centimeters a year. The East Pacific Rise is spreading very quickly. Here it's 18 centimeters a year, here it's 10, here it's 17. And part of the reason why you can have those variations is because of the transform faults. So this one could be moving at 10, and the next one over could be moving at 12. As long as you've got that transform fault, then they can move at different speeds. The other things shown here in red are the absolute plate motions relative to some fixed position inside of Earth. We're not going to worry about that. But we can definitely use GPS to determine where land has moved year after year after year. Now, hotspot volcanism was spoken about in the last video, but we're going to add this one in as well, just to make sure you're clear on it. So this is Hawaii, and we're looking at the big island of Hawaii here where there's active volcanoes. There's even a new volcano forming off the shore called Loihi, and that's going to be the next volcano because this whole chain is being fed by a mantle plume, and the plate is moving over that mantle plume. And hotspots provide an independent type of confirmation that plates are really moving. So here are three little cartoons with time 1, 2, and 3. Here's our mantle plume coming up and feeding the volcanic chain, and we get a volcano. The mantle plume stays where it is. The lithosphere moves. So this volcano, after some time, is now over here, and it's become extinct. It no longer has a magma source, and the active volcano now in this group is located over here. Time goes on a little more, and both of these move off to the left, and now we've got a new active volcano. And this one's extinct, this one's also extinct, and if it's been weathered below sea level, we actually call it a seamount. It's no longer an island. And so that's what's going on in Hawaii. This is the big island that's active right now. As you go back to Maui, Molokai, Oahu, those are extinct volcanoes that are no longer over the hotspot. Here's a cartoon showing that. Here's Hawaii, Maui, Oahu, Kauai. So the Pacific plate is moving in the direction that these arrows are showing, this way. The hotspot stays fixed. Here are many of the hotspots that are around the Earth today. Some of these you're going to plot on your plate tectonic map, and you can see in some cases the traces left behind from plate motion. So for example, here's that Hawaiian one, and the trace goes not only for a long time to the west here, northwest, but it actually continues all the way up into this trench. And the video that you just watched explained why that is. Here's another hotspot called Tristan da Cunha. And interesting, the hotspot has a trace going back to Africa and South America, suggesting that that hotspot actually had something to do with breaking up Pangaea, and it's been traced ever since. Iceland has two sources of volcanism. It's on the Mid-Atlantic Ridge, and it's also a hotspot. And again, we can see traces that suggest it might have been a hotspot that broke Greenland away from Eurasia. So many people believe that hotspots are fed from plumes of material that comes all the way from the core mantle boundary. But not everyone believes that. In fact, this is one of the big controversies in geology and plate tectonics today. Some people believe that the entire mantle convects. So here we've got our core, our crust, and we have the lithosphere and asthenosphere. Here would be those plumes coming all the way from the core mantle boundary, and they feed magma to the hotspot, the plate moves over it, and then the mantle is convecting in these large-scale convection zones. And we might even have subducting slabs go all the way down to the core mantle boundary and lay down there. In fact, some people have tried to image those, and it's called a slab graveyard down there. At least it's one interpretation of the data. But there are other people who do not believe that the mantle convects as an entire whole and believe that the mantle is layered. So here we have the asthenosphere representing its own region, and then we have the mesosphere. It's just another part of the mantle that does its own convecting but does not transfer any material up above. So this down here would make the mesosphere part of the mantle a closed system. If you remember, we talked about closed and open systems. And in this case, the hotspot volcanic source would be very shallow, and slabs that would go down in subduction zones wouldn't go beyond that particular layer. Which one's correct? I don't know. Maybe one of you will become a famous geologist and figure it out. So I asked you these questions quite a while ago when we started talking about plate tectonics, and I want to make sure everyone's clear on the answers. If the Earth's crust is broken into moving plates, what happens if these two plates move apart from each other? Is there a big hole in between? Well, I hope by now you realize that of course there isn't, but that is where new magma comes up and makes brand new seafloor, and we call those regions seafloor spreading areas. Is the Ring of Fire more than just a Johnny Cash song? Yeah, it is. We just talked about it. It's the ring of active volcanoes all the way around the Pacific Plate. How is ancient climate information preserved in rocks? And what can this tell us about the location of the continents in the past? Well, this is something we talked about in the first video of this whole series in Unit 3A.1. We talked about how evidence for ice ages and tropical climates and temperate climates are preserved in rocks based on the type of rocks that form, such as limestone or glacial deposits. And this tells us that the continents have moved from their past position. Why is Hawaii an active volcano? I promise I'll ask you this on the first exam. Because a lot of people put, well, it's by a subduction zone or it's a divergence zone. But no, Hawaii is nowhere near a plate boundary. In fact, it probably couldn't be farther from a plate boundary. It's right in the middle of the Pacific Plate. And it's active because it's over a hot spot. It's over one of those mantle plumes. It still tells us that the plate moves because we can see the change in age of islands as you move along. But it is not generated at a plate boundary. Now, I just showed you some exceptions like Iceland and Tristan da Cunha that are on the Mid-Atlantic Ridge and also hotspots, but that's certainly not the case for all hotspots. Coming up next, you're going to watch another video from City College of San Francisco about plate tectonics and California geology. Pay attention to the first half especially. The second half has a lot of stuff we haven't talked about. And then one last video from me.